Calculate the surface tension force exerted by water on a 2 mm diameter thick aluminum wire that is shaped into a square, with a side length of 1 meter. Also, what is the ratio of the surface tension force to the weight of the aluminum wire? What happens to that ratio if the wire thickness is increased to 10 mm? We'll need the following three constants to solve this problem. The mass density of aluminum wire, which is 2640 kg per meter cubed. The surface tension of water, which is 72.8 millinewtons per meter, which is equal to 0.0728 newtons per meter. And the gravitational constant of acceleration, which is 9.81 meters per second squared. The length of the square-shaped wire is simply equal to 4 times the length of one side of the square, or 4 meters. The surface tension force that is acting on the wire can be calculated as 2 times the surface tension coefficient of water times the length of the wire, which gives a surface tension force value of 0.5824 newtons. Note that the factor of 2 in the beginning of the expression is due to the fact that the wire has two circumferences, an internal and an external one. Even though the internal circumference is slightly shorter than the external one, due to the thickness of the wire, this small difference can be neglected, as compared to the total length of the wire. For case 1, the diameter of the wire is 2 mm, or 0.002 meters. The cross-sectional area of the wire is equal to pi times the radius of the wire squared, where the radius is equal to the diameter of the wire over 2. This gives the area as pi times 10 to the minus 6 meters squared. We can get the wire's volume by multiplying the length of the wire times its cross-sectional area. And so we get the wire's volume to be 4 pi times 10 to the minus 6 meters cubed. We can then get the weight of the wire by multiplying the wire's density times its volume times g. The weight of the wire is calculated to be equal to 0.325 newtons. Finally, the ratio of the surface tension force to the wire's weight is equal to 0.5824 newtons over 0.325 newtons, which is equal to 1.792. In case 2, the thickness of the wire is increased 5-fold, to 10 mm, or 0.01 meters. Increasing the thickness of the wire does not affect the length of the wire, or the surface tension force. The cross-sectional area of the wire, however, is increased by 5 squared, or 25. And therefore the volume of the wire is also increased 25 times. Which leads to a 25-fold increase in the weight of the wire. This causes the surface tension to weight ratio to become equal to 0.5824 newtons, divided by 25 times 0.325 newtons, or 8.125 newtons, which gives a ratio of 0.07168. One might erroneously think of a soap bubble as having a single surface. But in reality, a soap bubble has both an internal and an external surface that enclose a volume of soapy water, many water molecules across. Hence, if we were to cut a soap bubble in half, as we have shown here, we would find both an internal and an external peripheral length. The surface tension force acts on both peripheral lengths of the bubble. Hence the surface tension force on a soap bubble is equal to 2 times the surface tension coefficient times the circumference of the bubble's cross-section, or 2 pi times the bubble's radius. This can be simplified to 4 times the surface tension coefficient times pi times the bubble's radius. When the bubble is in equilibrium, meaning it is neither growing nor collapsing, the surface tension force on the bubble that tends to collapse the bubble is exactly balanced by a pressure force from within the bubble that tends to expand it. The pressure force on the bubble is equal to the difference between the bubble's internal pressure and the external atmospheric pressure times the projected area of the bubble, or pi, times the bubble's radius squared. At equilibrium, the surface tension force is equal to the pressure force. Substituting the values of the two forces, Fst and Fp, and simplifying the resulting expression, we get that at equilibrium, the pressure difference between the bubble's interior and exterior is equal to 4 times the surface tension coefficient divided by the bubble's radius. Both an air bubble in water and a droplet of water in air have a single surface, and hence the surface tension force acts on a single circumferential length for both the bubble and the droplet. Therefore the surface tension force that acts on the bubble or droplet is equal to the surface tension coefficient times the circumference of the bubble's cross-section, or 2 pi times the bubble's radius. Note that the factor next to gamma is 1, because there is only one surface. Recall from the previous slide on soap bubbles, that the factor was 2 because there are 2 surfaces for a soap bubble. Following a similar derivation to the one for the soap bubble, we find that at equilibrium, the pressure difference between the bubble's interior and exterior is equal to 2 times the surface tension coefficient divided by the bubble's radius. Calculate the pressure difference in atmospheres between the inside and outside of a bubble in water that is in equilibrium. The radius of the bubble is 0.1 micrometers. Given a bubble radius of 0.1 micrometers, or 10 to the power minus 7 meters, we can use the equation for equilibrium pressure inside a bubble or droplet to calculate the difference between the pressure inside and outside the bubble. The pressure difference is equal to 2 times the surface tension of water, which is 0.0728 newtons per meter, divided by the radius of the bubble, which is 10 to the power minus 7 meters. Performing the calculation gives a pressure difference of 1.456 megapascals. Next we convert 1.456 megapascals to atmospheres by dividing by the conversion factor of 0.101325 megapascals per atmosphere. We calculate that the pressure difference between the inside of the bubble and the outside of the bubble, that is required to keep a 0.1 micrometer radius bubble in equilibrium, is equal to 14.37 atmospheres. The contact angle of a liquid with a solid is the angle that the liquid's surface makes with that solid when the two are in contact. The angle is measured in the liquid, starting from the solid's surface. Depending on the value of the contact angle, the liquid can be fully wetting the solid at a contact angle of 0 degrees, or the liquid does not wet the solid at all at a contact angle of 180 degrees. The main factors that affect the value of the contact angle are the type of liquid that is at the interface, the type of solid that is at the interface, the type of fluid that is above the interface, which can be a gas, a vapor, or another liquid, and the ambient temperature. Some common contact angles, when air is present above the interface, and the ambient temperature is equal to 20 degrees Celsius, are as follows. The contact angle of water on glass, which is equal to about 25 degrees. And the contact angle of mercury on glass, which is equal to 140 degrees. You can use the slider to vary the contact angle, and visualize the shape of a liquid droplet on top of a solid surface. When you wish to continue with the lecture, please press the play button at the top. The contact angle has important applications. Hydrophobic solid materials. are materials that have a contact angle with water that is larger than 150 degrees. These materials are used to make waterproof fabric, like the raincoat and umbrella shown here. The high contact angle of these materials with water causes the latter to form droplets over the surface that can easily slide or fall off. The word hydrophobic literally means fear of water. Hydrophilic materials, on the other hand, have a small contact angle with water that is smaller than 30 degrees. Solid materials with a contact angle of nearly zero with water are used as coatings for self-cleaning glass, like the glass in the windows of a skyscraper. The word hydrophilic literally means love of water. Capillarity refers to the rise or fall of a liquid in a small diameter tube, due to the molecular interactions of the liquid with the wall of the tube. The surface tension force is equal to the liquid's surface tension coefficient, gamma, times the tube's circumference, which is 2 pi times the tube's radius. In order to get the surface tension force component in a direction parallel to the tube, we need to multiply the surface tension force by the cosine of the contact angle. We call this force the capillary force, or Fc for short. Note that the component of the capillary force that is perpendicular to the tube's surface cancels itself out, since it acts in opposite directions, from opposite sides of the tube's circumference. The pressure force acting on the liquid within the capillary tube is equal to the cross-sectional area of the tube, which is pi times the square of the tube's radius, times the fluid's density, times the gravitational acceleration, times the height of the fluid within the tube. When the liquid within a capillary tube is at equilibrium, the capillary force and the pressure force acting on it have to be equal. After equating the previously derived equation for the capillary force and the pressure force, we can simplify the resulting expression and conclude that the height of the fluid within the capillary tube is equal to 2 times the surface tension coefficient times the cosine of the contact angle divided by the fluid density times the gravitational acceleration times the radius of the capillary tube. Let us consider the case of capillary rise, such as the case of water with a glass capillary, where the contact angle is equal to about 25 degrees. In order for the liquid to rise within the capillary tube, or in other words in order for H to be positive, the cosine expression must be positive. This means that the contact angle must be less than 90 degrees. Let us consider the case of capillary depression, such as the case of mercury with a glass capillary, where the contact angle is equal to about 140 degrees. In order for the liquid to be depressed within the capillary tube, or in other words in order for H to be negative, the cosine expression must be negative. This means that the contact angle must be greater than 90 degrees. Capillarity has many everyday applications. The small channels and crevices within a sponge act like capillaries that pull water into the sponge. The paper fibers in paper towels also act like capillaries that pull water into the towel. And the capillary force in narrow tubes called xylem, in plants, along with other mechanisms, including osmotic pressure, help pull water from the soil up to the leaves. The surface tension coefficient of a liquid varies inversely with temperature. Shown here is a graph of the surface tension coefficient of water versus temperature. We can see from the graph That is, temperature increases, the surface tension coefficient decreases. The critical temperature of a substance is the temperature at which the gas and liquid phases of the substance are indistinguishable, and remain that way, no matter how much the pressure is increased. The critical temperature of water is 647 degrees Kelvin. When the temperature reaches the critical temperature of the liquid, the surface tension coefficient becomes equal to 0.